Good evening all. I am Udhaya Kumar, 4th year from Mechanical Engineering Department from Pratyusha Engineering College. I'm, I'm going to present a webinar about liquid fluoride thorium reactor, which means we use liquid as a fuel instead of a solid fuel rod. This is a future of nuclear power plant. Before going deep into this, we can see about the current energy consumption and what are all the fuel we use now. Okay, let's get started. First, consumption of world fuel in percentage. Uh, for developing countries, mostly we need energy. For producing energy, we need coal and other sources like solar, wind, and nuclear power plant. But mostly we use coal for the production of energy. In the organization says um, from 2017 and 2018, the energy consumption has increased by 2.9 percentage, and in the average of 1.9 percentage. That means from 10 years average, 1.5 percentage of the energy consumption has been increased, and simultaneously natural gas consumption has also increased by 2.0 percentage. Okay, consumption of coal. As we said, the main source of energy production is coal, and two main countries, which is a developing country, which use more amount of coal. Okay, China used 36 million ton equivalent of oil equivalent, and India used 16 million ton of oil equivalent. That means million ton of oil equivalent means the amount of coal extracted from the earth and amount of coal used for production of energy. That is MTOE. As we can see, China use more than India, and when compared to 2017, the coal consumption has been increased by 1.9 percentage, and one organization says SIA, that's the organization name, which states that when compared to 2018, in 2040, the energy consumption will be increased by 28 percentage with the means of coal, natural gas, oil. Okay, next to coal, the main energy server is wind, solar, and nuclear. We cannot trust solar and wind because it depends on the surroundings. Like if we have sunny days, the energy can be produced by a solar panel, and wind turbine can be only constructed in windy areas like mountain. So it is dependent on some surroundings. But nuclear energy can be trusted, and it can be reliable. It can produce energy continuously irrespective of the environment. But it is not in a full flow because many disaster has happened in the past. Example for in like Chernobyl in Russia and Fukushima in Japan and 3 Mile Island, which imprint the bad ideas about the nuclear power plant among the people. So okay, let's see the percentage. Wind and solar contributes 2.3 percentage, and nuclear power plant contributes 1.5 percentage. As we said, nuclear power plant is not in full flow because of the disaster which happened in the past. So okay, what if we add a fuel that is safe, and which is emit less CO2 emission and less cost, and which produce no waste, unlike a normal nuclear power plant, which is okay. Before seeing what the fuel is, we can look into what the problem in normal power plant, and how it is dangerous and how it can be overcome by this nuclear fuel. Okay, now we use conventional nuclear power plant. Okay, this is the layout of a normal nuclear power plant. It normally contains these parts: a core, a heat exchanger, and a turbine and a generator to produce electricity. A core is a main part which produce heat by the process of a fissile chain reaction, which we can look into later. A heat exchanger is used to transmit heat from one fluid to another, and a turbine is used to convert mechanical energy, which makes the generator spin and transform into electricity. Okay, this is the a simple layout of a normal nuclear power plant. Okay, This is the main part of normal nuclear power plant, which produce heat by the process of fissile reaction. Okay, it contains a normal dome-like structure which is made of graphite to prevent nuclear radiation to escape out of the surroundings. Okay, it normally contains of fuel rod. This is the fuel rod, as you can see, which is made up of uranium 225, uranium 238, or uranium 233. Commonly, uranium 235 and uranium 233, which is the preferable material that can be used as a fuel rod, which is immersed in a water. It's blue color, as you can see, which can be a normal water or a heavy water. In this case, we use light water, which means normal water, like a normal water. This whole setup, okay. First, first fissile material like extra neutron is made to bombard in this bombard this rod, which make the fissile reaction to continuous, which we can see later, and which due to this process. Um, the water gets heat up, and the heat is transferred to the heat exchanger, and which is coupled by a turbine and generator to make produce electricity. So okay, we can look deeper into the fissile reaction next slide. Okay, this is the basic process of fissile reaction. uh, this you can see like a ball like structure, which is the microscopic view of the fuel rod, which is one atom of uranium 235. uh, uh, Fuel rod can be either made by 235 or 233. In this case, it is 235. When one proton is bombarded with this isotopes, it split that isotopes into two and produce one more neutron, like this. When it is bombarded to this, it produce is split the isotopes and produce the nuclei. As it goes, it again bombarded into another isotopes and produce extra nuclei, and the chain reaction goes on. The use of moderator is the neutron which is bombarded will be so fast, so the rate of fission is so less. So to reduce the speed of the neutron, we use the moderator, like to slow down the moderator, like to slow down the neutron and to increase the chance of fissile that occurs in this process. So when it splits, it produces a large amount of heat, which heat the moderator and convert into steam, and that's convert into steam, and that which heats the water, and that heat is transferred to the heat exchanger, and that heat is transferred to another gases like helium, which heat helium, and that helium is made to impact on the turbine, and turbine rotates the generator, and electricity is produced. This is the basic process. Okay, we seen how it works. So we can know how it is dangerous. It is operated in high pressure. The normal conventional power plant is operated at high pressure because the water we use ordinary water as a moderator. Okay, okay. Uh, the ordinary water boils at 100 degrees Celsius. So by keeping that, we cannot turn the turbine. So we need high pressure. So increasing the pressure of the moderator, which means water, so it to rotate the turbine wheel. Okay, so it is so dangerous to operate, because if anything happens, high explosion can be occur, like occurred in Chernobyl. Okay, production radioactives. Okay, in this what are all the radioactive? It means plutonium, which will be on Earth for 1 million years, which stays radioactive for 1 million years. Okay, when the uranium splits, it produces it means it produces a subproduct, like a subproduct. It produces plutonium, which has 1 million half life year. That means it stays in the earth for more than 1 million years. So it is so dangerous. Okay, then the plant need to be maintained and refuel of the rods. If the uranium rods are used and no more uranium left, it need to be shut down for the maintenance and and the refuel of the fuel rods. They say a turbine can last up to 2 months and uranium can last up to 8 months. And the used fuel rod, when we change the used fuel rod, it need to be kept under the controlled environment like a tank which is covered by the water. Okay, it should not react with the ordinary environment, it should be preserved in the certain environment. So it is also a headache problem. So what if we not kept in the controlled environment? The hydrogen explosion can happen if the rod interact with the surroundings like oxygen. Some reaction take place and the hydrogen explosion can happen. So it is so dangerous. And many disaster happen like Chernobyl incident and 3 Mile Island and Fukushima Daiichi accident, which is recently happened in 2011 due to tsunami in Japan and created a bad imprint on public mind. So these are the dangerous situation and situation that can occur while using a normal conventional nuclear power plant. So how we can overcome this by using that fuel that we said before, we can see later. Okay, this is that fuel power plant called liquid fluoride thorium reactor, shortly called as lifter. Okay, which use a solid as liquid as a fuel, um, not like a fuel rod. Like it use liquid as a fuel. It does not use any control rod or something like that. Okay, we can look deeper into it. Okay, as we know, this thorium is the main fuel in this reactor, so we can take deeper look into it. Thorium has 90 atomic numbers, an half-life of 14.0 billion years. Uh, 14.0 billion years, and its boiling point is 478 degrees Celsius and melting point 1755 degrees Celsius. As you can see, it is first discovered in 1829, and many research has been going on into this from 80s, like Marie Curie, all of them research on this, but many not got interest in this because from a normal power plant we can uh, produce nuclear weapon from this, but in this we can't produce a nuclear weapon. So the olden days the nuclear weapon is the most priority, so they not much care about it. So we can go much deeper into it. Okay, thorium versus uranium. Okay, how much it is available in our earth? So let's see. Uranium has availability of 5.5 million tons in the overall earth, but only 0.72 can be used as a fuel, because 5.5 million tons is fully available like uranium 238, which cannot be used as a nuclear fuel. We need to be it need to be processed and something. Only 0.72 percentage is available as a nuclear fuel, which is uranium 233 and uranium 235. And thorium, let's see the availability of thorium. Availability of thorium is 6.6 million ton in the overall earth, but the interesting thing is the most of the thorium can be used as a fuel, as a nuclear fuel. Many countries has thorium reserves. In this, India has stopped with 963 million ton, and the United States, Australia, Canada, and South Africa, as we can see, all are tons. In this, India is the most abundant has the most abundant resource of thorium. Okay, so this type of reactor is very much is helpful for India, because we have lot of resources and we don't no need to um, bargain from other countries for uranium, because we already have a lot of thorium in our country. Okay, thorium, how we can use thorium as a fuel? the interesting part thing is the thorium cannot be used directly as a fuel. It need to undergo some process to be used as a nuclear fuel, which is simple. The interesting thing is the thorium need to take one neutron from other element to convert it into uranium 233, which is a which can be used as a nuclear fuel. Actually, thorium is not a fissile material, but it's a fertile material. Okay. First, the process goes like this. First, the thorium will take a neutron from uranium, either uranium or a plutonium. When it takes the proton from uranium or plutonium, thorium became thorium 232 became thorium 233 and palladium 233, and finally it became uranium, which can be used as a nuclear fuel. Okay, let's take a deeper look into it. This is the normal layout of liquid fluoride thorium reactor, and you can see the components. It is similar, but similar to normal conventional nuclear power plant, but it has extra safety measures and processing plant and refueling plant. The one is core, which produce heat, and the two is heat exchanger, and three is a generator and turbine, which is used to produce electricity, and four is jumper tank, and five is processing unit, and six is refueling tank, which will explain deeper in the later slide. Okay, working of lifter. So let's see first in the core what happens to the core, because because that's produce heat. Okay, that's the main part, like an engine. Okay, first into the core, fluoride salt is filled. The fully fluoride salt is filled, and in this graphite is used as a moderator. In the normal conventional nuclear power plant, water is used as a moderator, and you know the use of the moderator. Like it slows down the neutron and increase the chance of neutron to impact in the fuel rods. In this case, graphite is used as a moderator. Okay, first fluoride salt is filled fully in the core, and thorium 232 and uranium 233 is added into the fluoride salt. The proportion of 80% of thorium and 20% of uranium. Since uranium, we use only 20% of uranium. Okay, by using uranium and thorium, we produce more amount of uranium, which we can see later. Okay, first what happens means, when as I said before, as I said before, as I said before, when thorium takes one neutron from either uranium or plutonium, it converted into uranium. That means by using less amount of uranium, we transferring thorium into uranium, so we can use it as a fuel. Hope you can understand. Okay. First, okay, 80% of thorium, 20% of uranium is added to the fluoride salt. When one neutron from uranium is bombarded with the thorium, it undergoes that process. As I said before, thorium 232, plutonium, and it finally converted into uranium 233, which is a fissile material. Okay. Okay. First it bombards with thorium, and the thorium undergoes its process and finally converted into uranium 233. And when that uranium 233 is bombarded with another neutron, and like a normal conventional nuclear power plant, that neutron splits and splits into two and produce another nuclei. Okay, and and produce heat, and the process goes on. Now fluoride salts will fully converted into uranium by this process. During this process, when the fissile material splits, it produces a lot of heat. Due to this heat, that fluoride salt gets melt. Now that fluoride salt is fully contained uranium, due to this conversion process, um, fluoride salt get melts due to the more heat. Okay, the main advantage of this is you don't want to operate in high pressure, which we can cover later. Okay, um, it, the molten salt, now the fluoride salt get molten. Okay, now it passes through the heat exchanger and transfer it this heat into helium gas, and that helium gas get heated and passes through the turbine and generator to produce electricity. Okay, this is the process. Then what happens means uh, this mol this molten salt this molten salt again come come through this way 1 to 5. Okay, the molten salt contains uranium, so it need to be splitted. While this coming, the processing plant will split up the uranium from the salt, from the molten salt. Okay, it separate the uranium from the molten salt, and the salt will again goes, and the process continues. Uh, now thorium should be added. Thorium should be 6 is a refueling tank, because all the thorium is converted now into uranium. So for the process to continue, thorium should be added by this. We should we There is no need to stop the power plant for the refueling, like a normal conventional power plant. Like in this like normal conventional power plant, we shut down the power plant for refueling the fuel rod and maintenance work. But in this, we no need to shut down the power plant. just uh, just an online process, we can add the thorium while the power plant operates. So this is so conventional. So this is the how process goes. Okay, so for dumper tank, okay, if anything happens, like any disaster happens or a temperature increases in this core, there is a freeze plug which melts at a certain temperature. If the temperature of the core increases, this freeze plug automatically melts and allow the molten salt to flow into the dumper. So the reaction is utmost stop. Okay, there is no need to active monitoring of the system. It is so passive. uh, it will automatically shut down. And another thing is, uh, if the if the temperature increases, the molten salt tend to expand, so it will flow through this. If there is a gap, there will be there will be no time for the fissile reaction to take place. So this is how it works. So okay, how it can differ from a normal conventional plant, and how we can say this is safer. Okay, as I said, it uses molten salt, not using a solid fuel rod. So it is not a so it can't be exploded in normal fuel power plant. So it operates in high temperature. A normal conventional power plant operate at high temperature, because the water boils at 100 degrees Celsius. In this, we use salt. The salt has a boiling point of 2000 to 3000 degrees Celsius. So it can take up more heat without boiling. The more heat can be added to this system. Okay, waste in normal conventional nuclear power plant, waste production is more. Okay, like plutonium, which is stays on the earth for 1 million years and stays radioactive. And by using plutonium, we can also uh, produce nuclear weapons, which is so dangerous. uh, in this, there is no plutonium byproduct, so we can't produce any nuclear weapon. And in this, the byproduct production is kind of different. There is no production of plutonium. The byproduct uh, occurred in lifter is neodymium, molybdenum, storium, zirconium, rhodium, ruthenium, palladium, which will stay in earth for 60 to 100 years. So it is much safer. We can keep it in some storage time for 100 years, and it is after that it is safe. Okay, and most toxic byproduct produced in this process is cesium, which has 30 years of life. Because that means after 30 years, that radiative power of the cesium will be reduced to half. Okay, and another toxic byproduct is neptunium. Neptunium, okay, and neptunium has a large number of half life, so it need to be treated and converted into other product. Neptunium can be converted into plutonium, and that plutonium can be used as a fuel for lifter. As I said before, either uranium or plutonium can be used to used as a fuel to convert thorium into uranium. Uh, the process as we seen before. Okay, and the online refueling, as we said in 6, we can refuel thorium into the core uh, as the plant continuously operating. There is no need to shut down the plant. Okay, lifter don't require massive cooling because there is already it is in liquid state. Okay, is fully surrounded by liquid. Okay, like salt, molten salt. So it is there is no need for a more cooling system. It can be cooled by air cooled or some little amount of cooling system, so it can be placed anywhere. For a normal nuclear power plant, it should be placed near the sea or where water is more, but here this is no need. And and thorium has availability of 98000 tons. Okay, it has the most availability everywhere in the world. Okay, and India has the most abundant of it. So we no need to ask for other countries for uranium. So we can use our own resources for the production of energy, which will increase our economy. Okay, as I said before, there is no plutonium is produced in this, like no plutonium is produced in this reaction, so there is no possibility of creating of nuclear weapon. They can't create a nuclear weapon from this, but in old days the main part of main goal is to create nuclear weapons, so they preferred uranium instead of thorium. That's why the process of using this as a fuel has gone low. Now it is taking a pace. Okay, it consumes all of its fuel. In, okay, unlike a normal nuclear power plant, some fuel rods are left. But in this, we convert thorium fully into uranium, and that uranium can be used again to convert new thorium into uranium. So none of the fuel is left without consuming. All have been used. Okay. And uranium is recycling, and another major advantage of this is the by the byproduct produced in normal nuclear power plant is plutonium, which is so dangerous and can be used to produce nuclear weapons, and it stays in earth for more than 1 million years, and that can be used as a fuel here, which is used to convert thorium into uranium, and we seen that process before. Okay, and the thorium power plant operates at 45% thermal efficiency. It currently predicted that um, it can operate at 45% thermal efficiency, but the research has been going on in the turbine field and generator field, which when it is successful, the efficiency can be increased by 5%, and it is overall 50%. Okay, in the future it can be 50%. And there is no power plant operating in this method because now only the research is going on. But the research has started in 1958 in the USA, but they closed in 1978 because the main focus in that time was creating nuclear weapons. So now it's taking this. Okay, this power plant also some problems. Uh, if it has some advantage, likely it will have some disadvantage obviously. Okay, since we use salt in this, there will be a corrosion in the core. The salt will rust the corrosion, so it should be maintained. But the research has been going on, like how we can use a different material, or we can use increase the thickness of the core to control the corrosion. Okay, and there is a significant gap in the research and necessary material for lifter. Still the research has been going on. There is not yet concluded. Okay, post I said before, like a post processing unit which extract uranium from fluoride salt. Okay, and it then again used for converting of thorium into uranium. That plant has not viably constructed yet. The research has been going on, and some concept has been going on and told about it, since it has not consumed. Since we use only small amount of uranium, like thorium 80% and uranium 20%, that uranium should be mostly enriched, like should have a highly enriched uranium should be used in this process. Since we use only less amount of uranium, which is so expensive to extract, that it need to undergo lot of process to be enriched. Okay, and the percentage I just said, for example, like thorium 80% and the uranium 20%, but the calculation should be accurate. It will be vary. The calculation is so difficult to continue the fissile process. Like the calculation should be made, like how much thorium is needed, how much uranium is needed, that the whole thorium will be converted into uranium by the process that we seen before. That calculation is so difficult, and the scientists and the researchers have been working on this. Okay, how this power plant can be helpful for Indians. Okay, India, as I said before, India has the largest thorium resources among the world, 98000 tons, which is mainly found in Kerala in the form of monosite sand. And that monosite sand should be processed, and thorium can be extracted. Okay, when compared to world resources, thorium has 28 percentage of world thorium resources. Okay, it is a major part, and obviously we have only less amount of uranium. So why, instead of asking the other countries, we can use our own resources to produce power, which can increase our economy. And interesting thing is, in one cubic meter of sand, we can find 200 gram of thorium. And in India, this concept was first proposed by Omiji Baba, who is called as the father of Indian nuclear program, uh, which he proposed this idea in 1958. Okay, he, he proposed, but none of them was interested in it, because we was a controversy to the world. Around the world, they are using uranium, but we are doing researches in thorium, because the world needs nuclear weapons, so they are more conscious in uranium. So we started to follow the world, and we use uranium. But now, since we have more amount of thorium, we decided to research in lifter power plant, liquid fluoride thorium reactor. And on meeting, they asked the members of Indian nuclear program. They said, "What will you do if you want to start from the first?" They said, "We will research in the thorium reactor from the starting. They will not go to uranium." So okay, many things has changed, and the only way to change the people mind is to prove that a power plant is safe, which will probably lifter will prove to the people. Okay, thank you for this opportunity. Gopinath sir, HOD of Mechanical, Principal, Chairman. Thank you all.